Good day, everyone. I am Marsden Badlisan, and I am your lecturer for today's subject. Now, for today's topic, the topic is heat of fusion of ice and heat of vaporization of water. Now, in order for an object to exchange thermal energy, these objects should touch each other. There should be a contact so that thermal energy will be exchanged. Now, on a microscopic level, energy flows on both ways. On average, if we look at it in a macroscopic level, the energy flows on one way. Now, the temperature is the energy flows always. It is always flow. It always flow from hotter temperature to colder temperature. Now, if there is no flow of energy, then it means that there is a thermal equilibrium in the substance. Now, what we mean by thermal equilibrium is that the temperature on all points of the substance is the same. Now, for the when we have the energy heat Q of when an energy is added to a substance, and suppose we assume that there is no work done and no phase transition. Now the temperature rises by a factor of delta T, and the energy is just equal to the mass of that substance times the specific heat capacity of that substance times the change of the temperature. Now, by how much the temperature rises depends on the mass of the substance. The bigger the mass, the the harder it is to rise the temperature of that substance. It also depends on the type of substance. Now, for if we compare the specific heat capacity of the water to that of copper, the water is about 4,190 joules per kilogram, while copper is about, I think it's about 390 joules per kilogram. Correct me if I'm wrong. And here we have for phase transition basically means the change of state of matter. Now, whenever a substance undergoes a phase transition, energy is transferred into or out of the substance without causing a change in temperature. Now, um, in this w- uh, setting, we continually poured heat in the substance, but the temperature of the substance is doesn't change. It is because the energy that was poured into that substance is used to, for example, we have an ice. In order to rip this bond between molecules, because in a solid, these molecules are bond closer together. Now the energy that is we poured into the substance will be used to rip this the molecules apart. Now, some people would assume that when you heat a water and then by the some of the energy down is um, will be used to rip the molecules so that you have hydrogen and oxygen, but that is not true. But and what is really happening is that we just rip molecules from their closer bonds. So we have, for example, we have a solid and it transition into liquid or liquid to solid. Now for the heat and phase transition. Now, if you have a ice initially at negative 30 degrees Celsius, um, if you poured heat and energy into the ice, Initially, it will rise, its temperature will rise up, and if it approached 0 degrees Celsius, the temperature remains at zero until at some point that the energy that was poured into the ice is enough to have a phase transition. And now, if we compare the energy that are needed, the energy added to the ice to be in order for it to transition into liquid. If we compare it to the water, as it transition into steam, which is gas, the energy that we have to add is um, to the water in order for it to transition into um, gas is greater than the energy that we need to pour into the ice. Now, for at normal atmospheric pressure, the heat transfer Q in a phase change is just Q, which is equal to positive or minus m times L. Here we, for a positive ml, it just means that the energy is gained, wherein for negative m times L, negative sign means the energy is lost. Now, when liquid changes to gas or gas to liquid, I'm sorry for the error, when liquid changes to gas or gas to liquid, the we just use the subscript F, L sub F, which is just we call it the heat of fusion. Now, for water, it has a value of about 3.34 times 10 to the 5 raised to the power of 5 joules per kilogram at 0 degrees Celsius. Now, when liquid changes to gas or gas to liquid, L, we use the subscript V to denote that it is a heat of vaporization. Now, for water, it has a value of 2.256 I mean, megajoules per kilogram. Now I think you have to note the values of this of heat of fusion and heat of vaporization, because in the in your activity you will be using these values in order to compare your experimental value to that of the value that is the standard value for the heat of fusion and heat of vaporization. Now we discuss now the procedure of the experiment. Now for step one, we start by heating the steam generator with we put about 2/3 full of water over the electric stove, and we set the stove range to medium. Now for step two, we weigh and record the mass of the inner calorimeter cap with the stirrer, and we without the fiber ring. We take it out the fiber ring as, and then the mass that we recorded will be we record it in table 5.1 as under the M sub ICS. Then step three, we fill the inner calorimeter cup, this part of the diagram. We fill the inner calorimeter cup with stirrer with 1/2 full of water, and we weigh it. Then we record the mass that we get under M sub ICSW in table 5.1, which will be given to you by Sir um, Jingle and Sir Arrogancia. Then for step four, put the inner cup with the ring into the outer um, calorimeter. Um, because we take out this part and we fill it with water, one half full of water. Then after that, we take it back, we put it back into the outer calorimeter. Then we cover the calorimeter and place the stirrer and thermometer as shown in figure 5.1. Then we stir gently until equilibrium is reached. Then after some time, we record the temperature as T sub 1. Now for step 5, we record the temperature of ice in table 5.1 as T sub ice. And we select one or two small lumps of ice with a total mass of around 50 to 70 grams. Notice if you will calculate Onya, you will have to convert grams into kilograms. Then we after that we wipe the ice carefully and add it to the water quickly. We need to wipe the ice because if you have um, if you have ice that is already melted, that melted ice already gained some heat, and that will add to the error in our experiment if we will not wipe the ice carefully. Then we put it back quickly to the we put it quickly to the water so that no energy loss in the contact with the surroundings. Which then just after the temperature of the water has been recorded, of course we first have to record the temperature of the water inside the inner calorimeter cup. After that, we add some um, ice in it. Then we cover and stir carefully the mixture and observe the temperature. As soon as all the ice has melted, we record the equilibrium temperature as T sub 2. We record it in table 5.1. Then step 6, we carefully remove the inner cup, this part, with stirrer and water. Then we have to make sure that no water adheres to the thermometer. Then we weigh the inner cup with stirrer and water plus the melted ice as m sub I c as I. Then to find the actual mass of the ice, that is m sub I, we just subtract the mass of the inner calorimeter cup plus the stirrer plus the water and the melted ice. We subtract it with the mass of the inner calorimeter cup plus the stirrer and the water. And we record the data in table 5.2. Now for step 7, we place back the inner cup with stirrer and the contents into the calorimeter. Now for um, step 8, before we introduce the steam to the calorimeter, we record the temperature of the water in the inner cup as T sub IW. We and then we record also the temperature of the steam. Now we assume that the steam is about 100 degrees Celsius because basically um, when you transition from liquid to gas, which is the steam, the temperature of that is 100 degrees Celsius. Now, here is the diagram for that experiment, that part of the experiment. It is not given to you but in the activity sheet, but I just get it in the internet. I just stole it in the internet. Um, Now for step 9, connect a rubber tubing from the steam generator. This part is labeled as conical flask. Um, Connect our rubber tubing from the steam generator to the water trap. Here it is labeled as steam trap. Another one from the water trap to the calorimeter. This part, um, the we have to note that the rubber tubing from the steam generator to the water trap is longer than the rubber tube from the water trap to the calorimeter. Um, then we let the steam to flow from the steam generator to the calorimeter for about 1 minute, and then we record the temperature of the mixture as at this part we record the temperature of the mixture in the calorimeter as T sub F. Then step 10 is to remove the inner cup with stirrer and contents. Then we weigh it and calculate the mass of the steam. We denote it with the variable m sub f, m sub s. Um, then we just repeat it 3 times. Then we get the average. Now for the heat of fusion. Now here, energy was removed from the water to first melt the ice. Now, if you have the calorimeter, if you put the ice, it is not automatically it will not automatically gain. It will not. I mean, it will not warm up. First, um, it has to melt. The ice has to melt before it gains some energy. Now for the water which has the higher temperature, um, the water will lose some of its energy, and we denote it by this formula. The lost energy is just we denote it by a negative value because it lost some energy, equal to mass of the water times the specific heat of water times the change in the temperature. Now, um, here we perform the experiment in an isolated cup, and we assume that all of the energy lost by the warm water was used to melt the ice and warm up the ice. And we assume that no energy was absorbed by the calorimeter, but it is the energy was just absorbed by the melt ice and to warm up the ice. Then no energy flowed from the cup into the cooler air in the room. That's the reason why we have um, the cover of the calorimeter cup. Then the energy gained by the ice is just here, since the ice is cooler, it will gain the energy that was lost by the water, which has a higher temperature than the ice. Then the total energy gained by the ice is just m times L sub F, which is just the energy needed to convert the ice from solid into to melt the ice. And this second term is the energy needed to warm up the ice, which is just m times c times the change in temperature. Now we'll set the energy lost and energy used equation to be equal to each other. Then, therefore, the latent heat of fusion is just equal to this expression. Um, we just use a little bit of algebra. Then we can come up with the latent heat of fusion to be equal to this expression. Now for heat of vaporization, we just use the same argument to that of the heat of um, uh, to the heat of fusion. Now we assume here that the heat that was lost by the steam is absorbed by the water in the calorimeter, and assume that if um, only the water in the calorimeter gain the energy. Now, if by that assumption, we will arrive by this equation. The heat lost by the steam, which is just the expression for the um, left hand side will be um, the mass of the steam times the heat of vaporization. This is the um, energy needed to convert the steam from being a gas to liquid. Then we add some term, which is the gain lost by the steam, which times this specific heat capacity of the steam times the change of its temperature. Now, um, in the left hand side is lost. That's why we denote it by a negative. The loss of heat of the steam. Then on the right hand side is just gain of heat by the water, which is just equal to this expression, this part. Now we use a little bit of algebra to arrive in this form. Now, if for example, the energy that was lost by the steam is absorbed by is gained by the water and the calorimeter. Now the equation will change. We will add some another extra term, which is just the energy gained by the calorimeter, which is just the mass of the calorimeter, times this specific heat capacity of the calorimeter times the delta, the change of temperature of the calorimeter. Now, the change of um, uh, the heat temperature of the calorimeter is just equal to that of the change of the temperature of the water. Now that's for the assumption that the lost heat of the steam is gained by the water and the calorimeter. Now here in this expression, we assume that the only substance that gained the heat that was lost by the steam is just the water, and that's why we arrive in this expression. And that's all. Thank you.